All right, so we are still in Unit 1. We're in Chapter 5 in AP Stat. We were kind of recapping and reviewing basically the whole chapter up to this point, as well as hitting back on the means and the medians again and figuring out the importance of them. And I left us off with this problem because I didn't want to start in the middle of it. But what we were saying is, for example, let's suppose that we have 10,000 light bulbs of some kind of brand of light bulb are all installed in a factory, and an average life expectancy for the bulbs can most easily be found by noting how much time pass before exactly half of them need to be replaced. All right. The median is also useful in certain kinds of medical research just like this. All right, because what we're trying to figure out is how can we do this? When you're looking at this example, the idea is if 10,000 light bulbs, all right, are installed, because it's so much, an average life expectancy is better for these bulbs because there is a large quantity of them, and more than likely you aren't going to have one ridiculous outlier that's going to sway it too much because it's so close to the same. The median can also be useful in certain kinds of medical research, which is what we were getting at here. And it says, for example, to compare the relative strengths of different poisons. A scientist notes what dosage of each poison will result in the death of exactly half of the test animals. And the reason why this is important is, I think we hit on one before about like a mouse trying to get out of a trap, and I said the one it took like 24 hours, but all the others only took like 15 to get out of like the trap or the maze. Same idea here. A certain type of poison, for some reason or another, might end up taking one person, or I guess not person, one could only hope, but one animal longer before any kind of death might occur from it. So that outlier could sway the data. If one of the animals proves susceptible to that poison, the median lethal dose would be better to use than the average to average it all out. For the mean, while the median is often useful in descriptive statistics, and we normally call the mean we have the arithmetic mean, right, when we're talking about it, is most important for statistical inference and analysis. It is a very important one. It is used a ton, all right? Mean is used all the time. Most people understand that the average and the mean are basically the same thing, and the mean of a whole population is often denoted by that Greek symbol mu, all right? Whereas we said with a sample, it's normally denoted as x hat, right? So kind of recapping all this again. And for example, the mean value of the set of all houses in the U.S. might be around $56,400, right? But the mean of 100 randomly chosen houses might be 52,100, or it could be 63,800, or it could be 124,000. The point is, if I randomly chose 100 houses, the mean could be different for all of them, right? Because it's a sample. Depends on the sample that I choose. So, in statistics, we learn how to estimate a population mean from a sample mean. Basically, you take an estimate of it, is what you're doing, of that population. It's what this whole entire thing is going to be built up to, your whole course, all right, that we're talking about, the whole idea of a sample mean versus a population mean. It is literally the focus of our course. And throughout this course, the word sample often applies to a simple random sample, which you'll see abbreviated a ton as SRS. And a simple random sample is a sample selected in such a way that every possible sample of the desired size has an equal chance of being included. So if you want to pause the video and write this down, a simple random sample again is a sample that in such a way that every possible sample of the desired size that you want has an equal chance of being included. It is also true that each element of the population will have an equal chance of being included as well. So in the real world, this process of randomly selection, or any kind of random selection, is often very difficult to achieve. Okay, it just is. Making something totally random and unbiased. So please continue with caution with this. We will learn later that certain samples and their sample sizes, all right, are required in order to assume things about populations. You'll learn that you need at least a minimum. I can't just sit there and say, well, I have a sample of 5 people, so isn't that enough? A sample of 5 people. These 5 people that I asked this question to all said this. Was that good enough to say the whole population is? That's the stuff that we'll get to. But all of this will make more sense months from now, basically. All right. the mathematical mean we went over, it's the sum of all the values divided by the total number of values, right? That represents the sum of all the elements in this set. N is the total number of elements that are in that set, basically. And again, that is the Greek symbol for sigma, which means sum. So let's take a look at an example. Suppose that the numbers of unnecessary procedures recommended by 5 doctors in 1 month period are given by this set. So, unnecessary procedures by 5 different doctors, right there. All right, in just 1 month. We want to find the mean, and then we want to find the mean, right? So, let's use a calculator as we did before, and we just plug those into a set. So I press stat, right? I edit my list. Here's what I have in my list. If that's not the same thing, you clear it out, right? If there's stuff in there, you want to make sure you go up to L1 and you clear. So it's all empty, right? Go up. You do not delete. You press clear and enter, remember. You fill in what you have. So we fill in all of those. Press second in mode to go back to the main screen. That's like quitting. Press stat, arrow over to calc. We do one variable, statistics, and press enter. And we make sure that we are list 1, right? Our list 1 is L1. It's calculated, and it's where we put our list of variables. We go to calculate, and when we do, this is what we get. I got my mean right here. All right, that's your sample mean, 13. You scroll down a little farther, you get your median of 8, right? So now let's say it's discovered, and actually before we do that, look back here. Sample mean is 13, and the middle, or the median, is 8, right? So the difference between the two, but let's say it's discovered that the 5th doctor also recommended an additional 25 unnecessary procedures, all right? And it should read, now will the median and mean be affected? Sorry about that. So now, will the median and mean be affected? So right here, I'm adding an additional 25 unnecessary ones. So instead of this, right, that's what the 5th doctor did. I'm saying, you know what, let's add 25 to that. Is that going to change anything? So we plug this in our calculator. I'm just going to change the 33 to 55. So I go back to stat. I go back to edit, and that 33 right there, you know what I'm going to do? I'm just going to change it to 58. And then I quit out of there by pressing second mode. And then I press stat, arrow over, one variable statistics because we're only talking about one variable. I press enter. Here's what we got. L1 is where we put our list. So you go to calc, press enter. And as you do that, right, that is our sample mean. And our median is 8. So notice that the median stayed the same. Right, but what do we get here? I believe it was 13 before, and now it's 18. It changed the mean. All right, by that happening, by that number getting larger, it changed everything, but the middle didn't change. It's still the same. All right, that's what I'm saying here. Notice the median stayed the same. The number change did not alter the median, but it changed the mean. The mean, again, is sensitive, very sensitive to your change in values. Take a look at another example again. All right, we've been over this before. We talked about how the median isn't going to be as affected by outliers, but the mean is. The mean is very sensitive to everything. So suppose the salaries of 6 employees are, all right, listed right here. Here's the salary of all those employees, respectively. Find the mean salary. Okay, so we just go to the calculator to speed it up. We press stat, edit, I plug it all in. Remember to clear it all out. Plug all of your salaries in. Press stat, calc, so we go over to one variable stats. All right, we've been doing this, I don't know how long now, so I think we should know how to get there pretty fast. We have the mean salary of $18,000. So the sample mean that we have, their sample salary is $18,000. Now, what is the new mean salary if we increase every salary by $3,000? Every single salary increased by $3,000. Right? Every single one. I need you to understand this. So, every salary that I had is increased by 3. Every single one. All right? We press stat, right? Arrow over. We got our one variable stats. And notice that the salary also, the mean salary, also went up by 3,000 because everything was. All right, so that is something key that I want you to notice here. The sample mean is now 21,000. Notice that I had you add 3,000 to everything, every stinking one of them, and the mean also went up 3,000. Unlike the example before, when we just altered the one doctor from 33 to 58, I changed that and it changed the mean. But if I would have changed every single one and upped every single one by 25, the mean would have also went up by 25. So what if everyone received a 10% raise now? Okay? If everyone received a 10% raise, that's not adding the same amount, okay? Because everyone's salary is different. That 10% is based off each individual salary. So I'm not adding the same quantity to all of them. Technically, I am adding a quantity to all of them, but it's not going to be the same because it's a 10% raise on each. So this was their originals, and I give them all a 10% raise, right? 10% raise for each, just showing you, multiplying it by 10%, right, of all of them, so we can see what their new salary is if they all got a 10% raise. That gives us this to plug in, so we want to go to our list and we want to plug these values in. So we plug them into our table. So you plug them all in. By now we know where table is, I hope. We press stat, we arrow over, and notice that my original mean of the original problem was 18,000, and now our mean is 19,800. All right. Notice that the original mean was 18,000, and the new sample mean is 19,800, which is 10% more. So if you're adding the same number to each one, it goes up by the amount that you add, the mean. And if you multiply everything, all right, by a certain percentage, then you can take your original mean and multiply it by that percentage to get the new one as well. So I hope this helped you see that when you add the same constant to each value, it increases the mean and the median by that much. Both those. We didn't look at the median, but that is also increased as well. Multiplying each value by the same constant will multiply the mean and median by that. All right, those will also change. All right, so I hope that you saw that in here. When we come back, I will review some more concepts again about range, interquartile range, variance, and standard deviation.